Hey guys, back with the back half of our study guide. State one way in which transverse waves differ from longitudinal waves. It has everything to do with the disturbance and the direction that the wave travels. Transverse waves are going to be perpendicular. Remember, perpendicular form a right angle. So our disturbance is going to go up and down like this, and our wave is going to travel this way. So you can see that that looks like, if you turn it on its side, it's going to be a T, and T and transverse are going to go together. So transverse wave, the disturbance is perpendicular to the direction the wave travels. So the hand is going up and down, and the wave is traveling perpendicular to that. Longitudinal wave particles move parallel. So this was our slinky. When we did our slinky, we saw that when we had the disturbance, when we pumped that slinky, we saw the coils go parallel. One way I want you to remember that is there is several L's in parallel, and longitudinal starts and ends with an L. So if we can maybe put that trick together, that's going to help us remember that particles move parallel to the direction that the wave travels. Define the terms crest and trough and discuss how they relate to the wavelength of a wave. All right, so crest is the highest point on a transverse wave, and trough is the lowest point on a transverse wave. So crest and trough, and crest and trough. And the distance is between the crest and crest, or trough and trough. So it's the distance between one part of the wave and the next part of the same part on the next wave. So it's either crest to crest, trough trough for a transverse wave, or compression and compression, or rarefaction and rarefaction on a longitudinal wave. Okay. So which wave has more energy? A wave that has a small amplitude or a wave that has a large amplitude? All right, so here are my two waves. Here's wave number one, and let's change this color. And here's wave number two. All right, so there's my rest. My amplitude is the distance from rest to crest. Rest to crest. If you have a higher crest, the higher amplitude is going to have a higher crest and a lower trough. So amplitude is a maximum distance that a wave moves from its rest position. A large amplitude wave carries more energy than a small amplitude wave. So a larger amplitude wave is going to be a higher crest and lower trough than a low energy wave, like so. For each wave moving at the same speed, which one has a greater frequency? A wave that has a short wavelength or a wave that has a long wavelength? Well, frequency is the number of wavelengths that pass a point each second. When the frequency increases, the wavelength decreases. Like when we clap our hands. Crest, 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 clap, 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 clap. We have high frequency and a short wavelength. Increase frequency, decrease wavelength. Compared to when we would put our hands way out at our side and we had a really long wavelength. Okay, this is going to be really low frequency and a very long wavelength. So decrease frequency, increase the wavelength. Let's get rid of that. That's covering up that now. Okay, so you are going to need to know this picture. So pay attention to where your light source is coming in. Where is your light source? Is it on this side of the picture or is it on the other side of the picture? All right, so pay attention to that first. Okay, so you're going to be asked to label a picture that looks like this. Okay, so use the word bank. So we have our incident ray coming in. Incident, it's coming in. And this is our normal down here. This is our mirror. It's reflecting up. So everything on the inside is incident ray, angle of incident on the incoming side. So our incident ray comes in, bounces off. Let's change that color. Bounces off. So this is all reflected. This is our reflection ray, and this is our angle of reflection. So you're going to need to know incident, where it's coming in. Look for your light source, the incident ray and the angle of incident on the same side. Then we have everything is reflected. So we're going to have our reflection ray and our angle of reflection. And our normal, remember that's our imaginary line. Okay, that is drawn perpendicular to the surface. Okay, if the angle of incident is 30 degrees, what is the angle of reflection? What law supports this? The angle of reflection would then be 30 degrees. The law of reflection states that when a wave is reflected from a surface, the angle of reflection is equal to the angle of incident. So if the angle of incidence is 30, the angle of reflection is 30, also 30, going to be the same. If the angle of incident is 70, the angle of reflection is 70. The law of reflection supports this. Only EM waves can travel through space. Now this is a vacuum, also called a vacuum, right? Not a vacuum cleaner, a vacuum. That space between the sun, where our electromagnetic waves come to us through radiant energy. We cannot hear sound, no sound in space. Okay? That's why you cannot hear sound out in space. Can't hear someone scream in space because sound waves require particles to have that energy being transferred from one particle to the next. However, out in outer space, there are no particles, so you cannot hear any sound. So in a transverse wave, the measure of the distance from trough to trough is the wavelength. So once again, here's our picture. So here's trough to trough. That is your wavelength. In a longitudinal wave, the particles move parallel. There's all our L's, and there is our longitudinal. The distance from crest to the next crest is the wave's wavelength. The sun's energy can move through space because it travels as electromagnetic waves. The wavelength of a wave is the distance from crest to crest. A longitudinal wave makes particles in a medium move back and forth parallel to the wave movement. What is the relationship between amplitude and compressions in a longitudinal wave? So amplitude is going to be the amount of energy in that wave, correct? And so on a transverse wave, it's really easy to see because your crests are going to be higher and your troughs are going to be lower. But with our longitudinal waves, it's not quite as easy to see. So when we have a high amplitude wave, your compressions are going to be closer together. If we have a low amplitude wave, not as much energy, then the particles in compressions are going to be further apart. They're not going to be compressed as tightly together because there's not as much energy to do that. Name a longitudinal wave, that is sound. All right, so the final thing we looked at was in lesson 3, and we talked about absorption. So that is a transfer of some energy to the medium that it travels through. So the things that we talked about were our tinted windows. On the cars, we have that so that not all of the sunlight reaches the inside of the car. So that is absorbed. That's where we also had the black car is going to absorb all of the energy. That black construction paper versus a white construction paper, it absorbs. So it transfers some of the energy to the medium that it is traveling through. Transmission is going to be our clear windows, passage of light right through that object. So reflection is going to be our mirrors. It's going to bounce off of that surface. So in our car example from our book, it was the chrome on the car, you can see a reflection. It makes it shiny. Bounces right back off. Okay, we have refraction, changes speed when moving into a new medium. So that was when we had that pencil that appeared to change shape or change direction when it was sitting in water. So refraction, changing speed when moving into a new medium, because those mediums have different densities. So when we had that pencil, which was, on the first page of our study guide, we were traveling, look, that light wave was traveling from the air to the liquid, and it travels much faster through the air. So refractions is going to be spreading out around a barrier. So here comes your wave. Okay, refraction, diffraction around a barrier. So constructive interference. So these two are when two waves are coming like toward each other. So with a constructive, you're going to have crests that overlap crests. So when they meet, they actually meet on crest hitting each other, and at that moment, for that one wave, you're going to have a wave with greater amplitude, and then this wave's going to continue this way, and this wave's going to continue that way. But for that one wave, it is a greater amplitude than either one of those individually. So destructive, the big one that we might use on our daily life might be some noise canceling headphones. So instead of crests, when these two waves hit, they're not hitting crest and crest or trough and trough. You are having crests hitting the trough. And so you're going to be creating two waves that overlap with less amplitude, lowering that down to cancel, more canceling each other out. Okay, so that ends the study guide. So make sure that you are looking at your notebook pages. Make sure you are studying the McGraw-Hill definitions. Make sure that you do the Kahoot again. Make sure that you review using the quizzes. Whatever other strategy that you are going to use to prepare for your upcoming test, make sure you do that. And you guys got this. You rock. See you soon. Bye-bye.